Well, everyone, good afternoon. Welcome to the session, The Clean Mobility Revolution Starts Now. My name is Dale Brocious. I'm the Chief Executive Officer and Chief Commercialization Officer for IACME, the Composites Institute, based in the USA. So it's my pleasure to be your host for this session, very exciting session. So here we're talking about mobility, and particularly clean mobility. So the way that people and goods move, which sits at the heart of our economy and lifestyles. The mobility revolution underway already represents a US $2 trillion annual investment opportunity. Transportation, as it sits today, accounts for 14% of all global CO2 emissions. It is one of the few sectors where annual emissions continue to rise. So therefore it's necessary to transition to net zero, and our speakers today will address how that's going to happen. So all industries must join this clean mobility movement. And composite stakeholders, or composite stakeholders, since two of our speakers are British, are key players in this revolution. So for this session, I'm pleased to welcome onto stage our fantastic speakers. So first is Alan Banks, Lightweight Innovation Manager for Ford Motor Company. Alan has been recently named as Chairman of Composites UK. We'll also have joining us, welcome Alan. Also Andy Reynolds, Head of Zero-E Hydrogen Storage and Distribution Systems for Airbus in the UK. And we also have with us Vice President of Market Development for the Michigan Economic Development Corporation, Eric Schreffler. So MEDC is sponsoring this session, and I'm going to turn it over to Eric, and he's going to kick things off with us. So if we can roll the video. Thank you.
A culture of innovation that put the world on wheels and is now driving the next generation of transportation technologies. A legendary workforce that powers a statewide arsenal of innovation. A dynamic entrepreneurial ecosystem that captures the world's imagination and transforms concepts into creations. Vibrant communities and abundant natural resources that draw visitors from around the world, offering an unparalleled quality of life. For growth-minded companies looking for the right business environment for expansion or relocation, Pure Michigan means pure opportunity. A global supply chain located within 500 miles of 50% of the U.S. population with direct access to Canadian markets via 3 international border crossings. Access to the highest concentration of engineering talent in the U.S. and a skilled workforce among the top in the nation for advanced manufacturing. A statewide support network for startups, entrepreneurs, and small businesses with a technology sector among the fastest growing in the country for annual tech job growth. The global epicenter of mobility innovation, ranking #1 nationally in automotive and mobility research and development. An international destination for foreign direct investment from across the globe. Historic downtowns and dynamic cities where people want to live. Combining a cost of living among the lowest in the country with a quality of life among the highest. When it's time to plan for what's next for your business, discover Michigan and discover pure opportunity.
Good afternoon, everybody. It's a pleasure to be here. Thank you, Dale, for the kind introduction. On behalf of the Michigan Economic Development Corporation, I welcome you to today's session on the important role advanced composites will need to play in the clean mobility revolution. With 20% of U.S. auto production, more than 20 automotive OEMs, over 2,200 domestic and global suppliers, the evolution, growth, and health of the auto industry is as important to Michigan as it ever has been. The extraordinary shift from internal combustion engines to EVs is going to require an all-hands-on-deck effort to drive innovative, sustainable technologies to ensure a greener mobility future. In Michigan, industry, government, and academia are collaborating as never before to create the environment in which research, development, testing, and implementation will thrive. For those of you in the room today who have made an investment in Michigan, we thank you. For those who may be wondering about the opportunities that Michigan may afford your organization, please don't hesitate to find me or my colleagues, Vlatko and Bob, who are sitting here in the front row, after today's session. There's always room for more innovation partners, and Michigan is open for business. I hope you enjoyed the brief video outlining some of the things that make Michigan great, and I hope today's conversation will provide you with insights and ideas on how we can all move forward together. I appreciate your time, and now I'll turn it back over to my good friend Dale Brocious to kick off the session this afternoon. Thank you.
Thank you, Eric. So now I have the pleasure to introduce our first company speaker. It's Alan Banks, Lightweight Innovations Manager for Ford Motor Company and Chair of Composites UK. Alan, the floor is yours.
Oh, thank you for the introduction. So my name's Alan Banks, as you said. I'm the Lightweight Innovations Manager at Ford Motor Company. My role is to take out as much weight as possible out of our commercial vehicle range. When we start to think about commercial vehicles, we need to remember that the business model for a commercial vehicle is actually quite simple. The more you can carry, the more I charge you for it. It's as simple as that. With electrification and as we move towards autonomy, the vehicles are getting heavier. Most people's driving licenses are cut off at 3.5 ton if you're lucky enough to be born after 1990, which is a real problem. Because if you want to drive a heavier vehicle, you have to take a different license. So my role is to get as much weight as possible to improve the payload efficiency of our commercial vehicle range. And I'm going to take you through a couple of projects that we've been doing at Ford in the recent years. So this first one was called Class. People in the room would probably be like rolling their eyes now and thinking, he's not going to present that again, is he? So I presented this around the globe many times. This was a project that actually won the GEC Innovation Award in 2018, which we're very proud of. This component was supposed to be a 100% carbon fiber rendition of the fabricated part that you can see on the bottom right-hand side there of a rear suspension member for a Focus RS. So that's not my day job. As I said, I'm a commercial vehicle guy, but this kind of landed on my desk, and we were very keen to work on this because I'd never worked in composite materials before, so I was really eager to learn. And what we learned was we couldn't make it out of carbon fiber, not in its entirety. So after those sort of 2 years of this project, we realized that the goal that we had with this just wasn't really feasible. What we ended up with was a mix of carbon fiber material. So we had UD prepreg from the front to the end, but we had SMC on the areas where we need the sort of heavy geometry over molding a steel insert. So we had 3 different materials and 2 different resins that we compressed and molded to make this part. Now obviously the reason for doing this is because we make the unsprung weight a little bit better, so we improve the suspension performance, but we also make the vehicle performance a little bit better and we reduce its CO2 output because the vehicle's lighter. So we did a life cycle analysis on this, and I'm not going to go over that project in any detail, but I'll happily answer questions on it later, is we went over the life cycle analysis of this. And if you think of a Focus platform, that goes all the way from a basic Ford Focus that we have in Europe, all the way to some of the really high-end Lincoln derivatives that we sell in the US. So depending on the derivative you're going to have will depend on how much CO2 you actually save on that vehicle. So in the best case, we would get CO2 payback on a full LCA analysis using the Gabi software in just over 1.5 years. And on the worst case, if it's a really heavy vehicle, then we get CO2 payback in just over 3.75 years. Now, that was dependent on us being able to find a method of recycling the waste carbon fiber from the prepreg. Now, when we did that project, and it's written there in red at the bottom, we didn't really have that process. That was kind of a goal. Without that recycling of the waste material from the prepreg, those LCA numbers are quite a lot different. So the reason I bring that slide up is because I'm going to test your memories, because I'm going to come back to it later. So the project that I want to take you through today is this one. This one's called Chassis. This one is actually my day job, so I'm going to take you through what we did for the weight-saving capabilities of a suspension system for a transit van. So we've all got, you've all seen transit vans, the fastest vehicle in the world. It doesn't matter what you're driving. There's always one in your rear view mirror trying to get past you. So you can see the scale of the project that we had. So the steel part is on the left-hand side. That weighed just over 21 kilos. The picture second in from the left is the hybrid concept. So that's the CAD concept that we had. The picture second in from the right, that's the actual part that we made. So that part weighed 12.5 kilos, which was just over 40% weight saving, which is just remarkable. We're doing a investigation on if we didn't use carbon fiber for the top and the bottom pressing. Suppose we use flax. Could that work? If we use flax, we can get another roughly half a kilo out of it. So that would be a 42% weight save. So that's something that we're going to use as a follow-up. So that particular component is, you can see the makeup there. So we use high pressure die cast, what we call side rails. So they're the parts that the carbon fiber goes onto. Then we have a carbon fiber pre-preg upper and lower panel. They're 6-layer thick in various degrees. We have an SMC rear panel, as you can see there, with an aluminium front tube, as we call it. Now that we could have used glass or carbon fiber for that particular aluminium part, but it didn't really add much to the design, but it did add quite a lot of cost. So hence we went to an aluminium extrusion there. And you can tell from all of the processes there, we're not using anything that isn't mass producible. There's nothing within this design that we couldn't meet the volume requirements of a transit, which by the way is about 500,000 vehicles a year. That's a huge volume that we have for transit. We looked at the front lower control arm of that vehicle. The steel part again is on the left-hand side. It weighs just over 4 kilos. The picture in the middle is the CAD rendition of what we thought it would look like, and the part on the right-hand side is what it actually looks like. So that was just under 30% weight save. We were quite happy with that. Again, all of this, I'll go over the design makeup of that. So that's actually 3 materials, and we kind of learned our lessons from the class projects that you saw on the previous slide, because we use a mix of materials using steel and carbon fiber. This part uses a steel insert for what we call the puck, so that's where the suspension ball joint fits into. It could have been carbon fiber, but the brakes are in very, very close proximity to that, and the easiest way to do that for package was to maintain the steel ball joint attachment for that. So we kept that steel part. That's overmolded by the nylon with long glass fiber inner core, and then that whole thing is overmolded with a long carbon fiber outer core. Again in nylon. So again, we use forging for the steel. We've got injection molding for the composite materials. And again, absolutely no reason why you couldn't mass produce this part to satisfy the entire volume. Then we have the final component I'm going to take you through. That's our rear dead beam axle. So this is used on our front wheel drive vehicles. So unfortunately, you don't get those in the US. These are available in Europe and the rest of the world. The steel component that we use for this weighs just under 40 kilos, so a substantial amount of steel on those parts. The CAD rendition that's in the middle, we thought that would weigh about 19.7 kilos, actually weighed 18.7 when we finished. So we're really, really pleased with the performance of this part. That's a 53.2% weight reduction, which is just staggering. Usually at Ford Motor Company, if we wanted to save 10 kilos, we'd sell a close family member for that kind of weight. So to get, sort of a 53% weight saving out of one component is just incredible. So again, we use a process called pultrusion for the main beam, and if you've never seen pultrusion, I urge you to Google it. It's basically witchcraft. It's having quite a lot of glass, carbon, and actually different sections of carbon goes through a resin bath, and then it all goes through a lot of dyes before it comes out in that shape. Importantly, you can see the picture that's in section where you can see all the labels to. That's the only beam we make, and that comes out in constant sections, and you can make that section as long as you want. If you wanted to make it 30 kilometers long, you can make it 30 kilometers long. As long as you don't change the section, you just keep producing. You just let the machine go. And we're really pleased with this part. As you can see in the picture on the far right, you can see all the different layers of materials that go through that. So again, we use aluminium extrusions, and we use fine blanking for some of the other parts that we have that are attached to it, or that are structurally adhered to it. And again, there's nothing within that design that we couldn't mass produce. Everything is entirely mass producible. You're probably wondering what the costs are for this. So this was a research project more than anything else, but there's nothing really why we can't sort of mass produce these, as long as there's a will to do it. Because we use some relatively unknown processes for Ford, our cost target that we had for this was $9 per kilo. So for every kilo that we save, we allowed the team to spend $9 to get that weight out. Honestly, we probably wouldn't spend that in production, but we do have a really good idea of where we would get that cost out. And all of these parts, by the way, have been on our test rig. The supplier that we had for these parts is exactly the same supplier that makes the steel parts for production. So all of these parts went on to their internal test rigs, that we've had them on test vehicles at our test track in Lommel, and they've all performed really well. In fact, the subframe and the dead beam outperformed their steel counterparts so much, they're clearly over-designed. So we have the opportunity to either change some of the materials for less expensive materials, or we can take even more weight out, because they massively outperform their steel counterparts. So in summary of this, and there's only a few slides left, you'll be very pleased to know, we spend about 69.3 kilos for the steel parts. The aim of this project was to reduce the weight by 40%, which is very, very aggressive. But we actually achieved a 46% weight saving. And we're really pleased with the result. It's just under 32 kilos for the entire system. And obviously, when we do this kind of thing, we want to increase the payload efficiency of the van, because that's our business model. But we are living in a world now, and there's no getting away from it. We are very focused on sustainability, and rightly so. We are entering a period of customer demographic who will not tolerate single-use plastic bags anymore. We can't do that. And this is the same demographic that is going to be buying our products in the future, and they will not tolerate unsustainable vehicles. They just won't. And this is something that we need to embrace. So when we were designing these, obviously we're looking at the sustainability aspect. So we did the life cycle analysis, as we did before. The front subframe, compared to its steel counterpart, would get CO2 payback in about 3.5 years, mainly because of the amount of pre-preg that we have in that. As you know, sort of pre-preg CO2, the energy embedment to make pre-preg is quite high. The lower control arm would get payback in just over a year. Again, that's mainly glass, and that has a much lower embedded energy in its production. But the star of this particular show is the rear dead beam. We get payback in just over half a year of that part. And that's mainly because there's a lot of glass in there, obviously, but the sheer amount of weight that we saved is just incredible. Now, that's a cradle to grave approach. I am desperately trying to convince our folks at Ford and our supplier base that we've got to stop thinking in terms of cradle to grave. We've got to start thinking about cradle to cradle. If we can't make these materials circular, frankly, we've all failed, and there's work to do there. So one of the things that I want to take you through now is some of the work that we did with a company called B&M Longworth. They actually have a stand in Hall 5 on the Signet Tech Skimp stand. I urge you to go and see it, because this is technology that is going to change the way that we do business in composite materials. So I'm going to start with the middle pictures before anything else. So this is the lower control arm. This process uses steam decompression to strip the resin from the fibers. And because it's only using steam, it just cleans the fibers. It doesn't damage them in any way. It leaves them absolutely pristine. So if they were pristine fiber when they went in, they're going to be pristine fiber when they come out. The lower control arm is co-molded with glass and carbon, as you saw. And I had always assumed that if we were going to put this into production and I needed to be responsible for the recycling of it, I'd have to redesign that part, because how do I separate glass and carbon if I want to reuse the material? I showed this to B&M Longworth and said, I'm going to have to design this. They said, well, we're not sure about that. Send us the parts and we'll have a look for you. So they put that through their decon process, as you can see here, and the resin stripped straight off, and what we've left with is the glass and the carbon in its purest form, as you can see there. Now, they are sort of commingled because that's how we molded them. So we need to find a way of separating those materials so that we don't contaminate the carbon with the glass and the glass with the carbon. We don't think that's undoable. We just haven't had to look at it yet. The picture on the right-hand side is an offcut of the rear dead beam axle you can see there. That went through the decon process, and all the fibres on the top of that, they're the carbon, and all the fibres on the bottom, that's the glass. The glass doesn't look particularly pristine, but that's just the way that the light was reflecting from the background. And interestingly, the piece of woven material that they put through their process is still woven, even after the resin's been stripped from it. So basically, what you put in is what you get out. Normally, you would chop down some of that material to make it more viable for the process. It makes it faster. So if you wanted to put this material back into SMC or BMC, you can. But the dead beam's 1.8 meters long. And we have continual strand fiber in that material. You can put a 2 meter length component in the decon machine. So if you wanted to, you could get 1.8 meter long fiber out of it. If you could find a secondary use for long fiber, you can get long fiber out. The picture on the right-hand side, on the left-hand side, which is the one I want to get to last, that's made of sort of pre-preg carbon top and bottom, as I said. Now, the way the industry uses pre-preg at the moment is when they scrap that material, they can't put it into the ground. You can't put uncured resin into landfill. So it's cured first, just so that it can be ground up to be put in the ground. Think about that. This is material that you bought, you've got an offcut, you cure it, and then you grind it and you throw it away. Doesn't make any sense to me. So one of the challenges that we gave Longworth was, okay, we know that you can reclaim the resins and the fibers from cured material. What about uncured? Because it doesn't make any sense to cure the material just to throw it away. So we gave them a piece of uncured material, and there it is, worked perfectly. So this is a real sustainable process that we think can solve a lot of the industry problems, especially from aerospace, from high-end motorsport, where the scrap rates from some of the materials can be absolutely huge. And this is material that you've paid for. Why wouldn't you recover it and then reuse it as something else? Or at least, even if you gave this material away for a second use, you're going to be more profitable. It costs you £121 in Britain to send material to landfill, £121 per tonne. So if you're sending that material to landfill, you could sell it to me for £50 and you're £70 better off. And we get the material for free to use in the reclamation process. We're really keen that this process is going to work. And as I said, I really urge you to go and see the stand in Hall 5. I'm going to quickly wrap up. So this is the project I've got going at the moment. This is called E-Shadow, so Electrified Structural Hybrid Automotive Designs for Optimised Weight. And yes, we do spend more time thinking of an acronym for the cool word than we do actually working on the project, as you might imagine. This is a project that we're doing with a UK consortium to try and get 40% of the weight out of the ladder frame for a transit van conversion vehicle. Those of you who have seen the amount of commercial vehicles on the road these days you could be forgiven for thinking that Ford invented COVID, because we've sold more transit vans than we've ever sold in our life. In fact, just to give you a flavour of that, the best-selling vehicle in Britain last year was a Ford Transit. Not the best-selling van, best-selling vehicle. Outsold the next best-selling car by 40,000 units. So it's really important that we can maximise the weight efficiency for our converters. So this vehicle will ultimately become, we're hoping, a supermarket delivery vehicle. So if we can get another 100 kilos in the back of that, which is kind of the weight target that we're going for with this, we're going to be really happy about it. So this project is about halfway through. We're hoping to see some parts come off tool at the beginning of next year, maybe the end of this year if we're lucky. But it's going really, really well. And I'm hoping that the next time I come back to JEC, I can give you some more details on this one. So I'm going to be quiet. I've got 20 seconds left. So that's me. I'll happily take questions at the end of this. And if you've got anything you want any more details on, you can find me on the UK pavilion, or obviously come and find me afterwards. Thank you very much.
Thank you, Alan. As Alan mentioned, we will have a bit of a Q&A session after Andy's presentation, so be thinking of the questions you'd like to ask him. I certainly have been thinking about them. So our next speaker, we're going to go from the ground to the air, is Andy Reynolds, who's the head of the Gt CO2e initiative at Airbus. So Andy, up to you.
Thank you very much. Thank you. And I must first of all say there was an awful lot of composite content in that, and there was an awful lot of science, or science we saw. Neither of those are going to be present in my presentation today. So I'll get that out there first of all. So, here it comes. There we go. So, my name is Andy Reynolds, and I'm leading all of the hydrogen activities that are part of the Gt CO2e project that is launched by Airbus. So we are looking to put an aircraft like the one you see on the screen into service in about 2035. So we could be flying, I could be flying back to Bristol or off to Toulouse, as I will be in a couple of hours, on an aircraft such as this. And the target really is not to reduce the emissions, and the climate impact, but to bring it to zero. And I'm going to talk to you a little bit about how we're going to do that. The impetus, as we were just hearing, I mean, it's for the whole of society is addressing this challenge about climate change, and transport is something that everyone is looking at. Aviation is something in particular that everyone is looking at. It's a very, very visible and focused on aspect of climate change. And we feel that. We feel, to be honest, as Alan was just saying, a moral obligation really to deal with the impact that our products have on the climate. Aviation is something that links the whole world together. Many, many of us will have flown here to be together and to have the exchanges we have, to do business with each other, to see our relatives, to reconnect as we have been doing over the last few weeks and months after the last 2 years. And we know how much we've missed that connection over the last 2 years. So we really want aviation to be something that is back and something that you can do and benefit from without any feeling of guilt or any impact on the climate at all. So those are the things that all of the governments have been doing with the COP26 last year in the UK in November. We see all of the major economies coming together, including India, including China now, with very challenging objectives for themselves. And then these are the challenges that we have given ourselves within the aviation industry. It's been something that has been going for a number of years, but in October last year, almost all, so 83% of or airlines that represent 83% of the traffic in the world came together and said, we're going to give ourselves the challenge that by 2050, we're going to reach net zero for aviation as a whole. And we're engaging with that, and we have a plan to deliver that. The plan has got many parts to it. It's a pretty challenging thing to do. Airbus by itself has getting on for 20,000 aircraft already in the fleet. Those aircraft, many of them are going to be flying for many years to come. We won't be changing them to run on hydrogen. So they will need to be developed, or they will need to be using a fuel that has close to zero impact on the climate. So there will be a lot of work going on in terms of sustainable aviation fuel. All of Airbus's aircraft today, all of the ones that are being delivered today, and many of the ones that are flying, are already certified to use a blend of 50% sustainable aviation fuel. The only problem with that is you can't get your hands on 50% sustainable aviation fuel. So we'll have to work with governments and with suppliers to deliver that. Boeing has set the target of having 100% sustainable aviation fuel aircraft by 2030, and I can tell you that Airbus always beats Boeing, so we will be doing it before then. It will still be a challenge to get hold of that sustainable aviation fuel. Today, most of it comes from biomass generated fuel, so oils, waste products from the cooking industry, sugarcane, all sorts of things that can be used to be grown and then converted into a sustainable aviation fuel. You reach a limit in the area of the Earth that you want to be dedicating to doing that. And we're able to do that today, but we will not be able to do 100% of the fuel for the fleet. So we will have to use an alternative technology, and we'll have to go to synthetic fuels. And if we're going to use synthetic fuels, you're going to be actually pulling carbon out of the air, either as it's produced, coming out of chimneys, pulling the CO2 out, and creating green hydrogen, fusing those things together and manufacturing PTL. If you want to do that, and you want to do it in a way that doesn't impact the climate, you need energy. You need green energy, and you need lots of it, and we'll see that in the next slide. This isn't a thing that's going to be for aviation. It's a thing that's going to be for the whole of society. The whole of society is going to need fantastic quantities of green energy over the coming decades for this and for many other industries as well that rely on electricity. Probably to heat our homes, to run our homes, to run many of our industries in the future. So one of the things that we are focused on is making sure that Airbus and the aviation industry has its share of green energy. If you're going to produce PTL, you're going to need to produce hydrogen. And we believe that as well as producing PTL and supplying that fleet which is existing today, you can take some of that hydrogen and put it directly onto aircraft and use it directly without producing PTL. And that's what the project that I'm working on and leading is all about. Here's just, before we get onto that, a little chart which comes from the International Energy Association of where we are today in terms of energy. So you can see that over the next 30 years, they're predicting that we will more than double the world's requirement for electricity. And in that time, we need to make a conversion from coal, from oil, from gas, towards sustainable sources of electricity. And that is an enormous challenge for the governments and for all of the agencies around the earth to make that transition. It will require a huge investment. But it's a huge opportunity. If you happen to have a few spare billions and you want to invest in the land and the infrastructure to do that, I believe there's an enormous amount of money to be made for the people who can do it. And some of the people who are producing petroleum today are in the perfect parts of the world to be harvesting sunlight and producing green electricity. And I believe they have the vision to do it. These are the aircraft that we have proposed and that we're working on very, very actively. And I can tell you the investments that Airbus are making directly in this are absolutely eye-watering for the state of where we are. If I'm saying these things are going into service in the middle of the next decade. So we're at very, very early levels of development today, but we are investing hundreds of millions of euros. I'm not joking when I say that, hundreds of millions going into these aircraft on an annual basis. You've got three different aircraft there. You've got the turboprop at the top, which is probably the one that you'll expect to see maybe earliest. Probably not able to take, or heading up towards 100 people we're trying to get to, and heading up towards about 1,000 nautical miles. The biggest aircraft today, A350s, 787s, they can fly for 7, 8, 9,000 nautical miles. But the vast majority of journeys that are made by aviation are less than 1,000 nautical miles. Almost the whole aviation industry around Europe, all of EasyJet and Air France flying around Europe, all around Asia, a lot of the stuff in the States, you're in the 1,000 nautical mile range. There's a huge market addressable by that product. We've got something else we're working on which is very attractive from an aerodynamic perspective with the blended wing body. Very, very innovative and very, very challenging, something that many people will have seen in various forums over the years, but something that brings a lot of opportunity in terms of storing hydrogen and gives us some interesting ways of looking at the architecture of the plane and finding places to put the tanks, which is the main challenge. And then at the bottom, something that looks a lot more like an aircraft that we're used to seeing and we're used to getting on board. That aircraft has the capability to go further, to be heading up towards 200 people maybe, and up towards 2,000 nautical miles. That one would have large tanks at the rear of the fuselage, and then links to turbofans rather than props. So something that looks a lot more similar. But we're working on all of those things together, and really my job at the moment is to lead all of the technology work to make sure that we're ready and that we have the ability to refuel the aircraft in roughly the same amount of time it takes to refuel an aircraft today, store that fuel for hours at a time so you can refuel the aircraft and come back to it the next morning and just go and fly, store it safely, be able to maintain the aircraft, distribute the fuel, and then burn it. And then just to give you a little bit more on the first aircraft that we've got there. So this is the turboprop aircraft. So you can see in sections 2 pretty large tanks at the rear of the fuselage. They're going to be liquid hydrogen, so cryogenic hydrogen storage tanks, only at a few bar, but at 20 K, so or less. So less than minus 250 C. I don't know that in Fahrenheit. I need to learn that in Fahrenheit, don't I? But yeah, 20 Kelvin in double-walled tanks. Today, I must admit, standing in front of a room full of composite enthusiasts, that tank on the first aircraft is almost certainly going to be an aluminium tank. But double-walled with a vacuum in between the two walls, a very high degree of vacuum with MLI, the same technology that you would see on rockets going into space for liquid helium tanks and things like that. So 2 of them for redundancy and in terms of the safety case to make sure that we are able to continue flight if there's any failures. And then a liquid distribution system, so actually distributing liquid hydrogen throughout the aircraft with, again, double-walled pipes, insulated in between the 2 walls with vacuum, with the vibration, with the challenge of all of the different flexibility that you see, landing, taking off, all of those shock loads, having to deal with that, maintain the temperatures, maintain the vacuum. It's a bit of a challenge, I can tell you. And then on this particular aircraft, we would have a fuel cell supplementing potentially a turbo fan. We've already got some fuel cell technology. We have a joint venture which we've set up, and we've already got fuel cells running, not quite at the megawatt scale yet, but getting up towards that level. And we're doing a huge amount of research to try and be ready for something that would be something with a fuel cell, but also looking at a direct burn. And then a motor on the front and a fan on the top. With that arrangement, you have a huge amount of heat being generated. The fuel cells are pretty efficient, the motors are very efficient, but you don't have to be very inefficient to generate a lot of heat. So one of the big challenges with that engine arrangement is to deal with the heat. When you have a turbojet, the heat goes out the back, and you don't, it's part of the joy of flying. But we would have to deal with that heat. So there's a lot of challenges in there, but it's a very, very exciting opportunity. We don't have very much carbon inside the hydrogen system today. I would very much like to move away from an aluminium tank and get towards a composite tank, but the technology isn't quite there yet today, even in the timeframes that we're looking at for cryogenic hydrogen with the dormancy time that we want. But we saw that energy demand. We know that even with the reductions in clean energy prices, which are happening today, really severe reductions in the price of clean energy, it will still be very expensive to make green hydrogen. And our airline customers are already very, very interested in fuel burn reduction. And that's the main reason that we put carbon on board the aircraft today, is to reduce the weight and reduce the fuel burn. That will be even more important in the future. So there will be an even stronger drive to make the aircraft lighter, more aerodynamically efficient, with cleverer systems able to respond more quickly, more flexibility in the wings, everything that we can throw at it to try and reduce the amount of fuel that is burnt. Even if the fuel is not directly impacting the climate, we still don't want to have to pay for it, and neither do our airline customers. So we will need composites on board that aircraft to deliver the best aircraft that we possibly can, because the hydrogen system is so difficult. We have a lot of research going on. This is a panel that, a cover that's been developed in the UK with the National Composite Centre, with ourselves and a number of other people. We've got a whole wing box demonstrated there, which this is contributing to, but we have composite research going on throughout the aircraft, in the fuselage, in the empennage, focused on that ability to take weight out of the aircraft, but by also reducing the cost of manufacturing, reducing the energy needs to do that, and making sure that we can do it at rate. So we want to be able to produce these aircraft at high rate. This isn't an A350 where we do 10 a month. This is supposed to be getting towards the A320 where we produce 70 a month. 2 or 3 A320s are produced every day. That's the scale of things that we do, and we need to be able to replicate that with this composite. We also need to be dealing with the life cycle. It's a different challenge with aerospace. The amount of CO2 that's pumped into the atmosphere during the lifetime of an aircraft is about 1,000 times more than the amount of CO2 that's pumped into the atmosphere during the manufacturing of today's planes. We put that into our financial declarations in the last couple of years. So for us, the focus is on reducing the fuel burn, because that's where the majority of the climate impact is. Nonetheless, we need those processes to be as green as possible, and you're absolutely right. Today, we waste a horrible amount of carbon, and the carbon that we put on the aircraft is completely unrecyclable today, and we must work at that. So that's for the primary structure, and also for all of the structure within the cabin, where it's probably a little bit easier, but still challenging. So the primary focus is on weight and aerodynamics and getting the fuel burn down, but we also have a very strong drive on life cycle, on recyclability, on reuse, and on green fibers and resins up front, because today the stuff isn't very nice. We'd like to escape that. And that is, ladies and gentlemen, all I was going to say. Thank you very much.
We have now time for some questions and answers. We do have a couple of roving microphones positioned at the back of the room, so if you raise your hand, someone will bring you a microphone. Please introduce yourself, and then we'll be able to ask your question. Yeah, we've got one here in the front. Come on.
Hi, my name is Garrett Kalkoffen from Carbon Truck and Trailer. I have a question for you, Alan, as you might expect. If you can tell us a bit more about your eShadow project, and whether or not the other parts that you mentioned in pultrusion in your witchcraft process, when those would be going into production, because I'd be really interested in learning more about that. Thanks.
Yeah, no problem. So I think when it comes to eShadow, we are probably looking for pultrusion for material manufacture rather than part manufacture. But pultrusion, for me, is a great process. I mean, when you think of the amount of components you have on a vehicle that are beams, especially on a trailer, when you have a constant section, for me, it's kind of the obvious choice. If you only want to work in composite material, I mean, you can put metallics through it as well, but there's no reason why you wouldn't just leave it running. I mean, the beauty of it is, I mean, seriously, you need to have a look at the internet to see it running. I've got some good pictures on another presentation, which I didn't have time for here. But if you can imagine, you've just got all of the bobbins, you've got all of the toes and the rovings, and they just are pulled through a set of dies, through a resin bath, and it's all cured, and it just comes out in constant section. There's quite a lot of barriers that are made for the roadside and things like that are made in pultrusion, because it's the obvious thing to do. Once the machine's running, it's completely unmanned. You just make sure that the material doesn't run out, and it just automatic, it pulls the material through, cuts it to length, puts it in a bin, and then you can take it where you want. I really like it for, I mean, when you consider what's on the vehicle, so we've got cross-car beams that hold the steering column, we've got sort of side rails that carry the structure of the vehicle and the battery these days. If you can make them constant section, why wouldn't you? Then you can use relatively expensive materials in an inexpensive way to save a lot of weight, to improve your structure, to make the vehicle last longer. For me, it's just the obvious thing to do. eShadow, as I said, eShadow is probably going to be using quite a lot of compression molding. We're still going to be using a lot of carbon and aluminium in that structure. But that is going to be a production vehicle, so the cost for that need to be a lot lower. We need to be bringing that in about half the cost that we were doing for the chassis project. But yeah, I mean, I am really into using some really high-end processes, some really, sort of innovative materials, and use them in an innovative way, because there's no hiding from it. The vehicles are going to get more expensive as we start to introduce lower weight. Unfortunately, you don't get that for free. But if we do it properly and we do it with like science, and we really make sure that we can deploy the material where we need it. We've got a mantra which is the right material in the right place. If we need pre-preg UD, we'll use pre-preg UD, but in the space we need it. So rather than make the whole transit out of carbon fibre, which I would personally love, but no one's going to be able to afford £150,000 for their transit. That's the kind of thing we need to be very specific to make sure the material stays in the right place.
Thank you, Alan. Do we have another question from the audience? Andy, I just want to ask you, is there a transition point where it makes more sense to use combustion for hydrogen versus fuel cells? I mean, how do you do those trades?
It's a challenge for sure. I mean, I think there's definitely a question today with fuel cells in terms of the scalability, whether you can move up from the sort of power that we're working with today, which is aiming to get to a megawatt scale but not yet demonstrated. When you start to talking about 200-seater aircraft and going thousands of miles, you're going to go quite a long way beyond that. So you're going to be, with today's technology as far as we can see it, if you want to go up towards the larger aircraft that would be going transatlantic or coast to coast, you're probably going to be looking at combustion technology today. We need to bring our friends in the engine suppliers with us. They're not always completely convinced that they need, but they need to make the investments, and they are making the investments in the combustor technology to be able to transfer from kerosene to hydrogen.
Okay, thank you. We have a question over here.
I'm Thomas Jacopin from Quantitech. I was wondering for you, Alan, as you were talking about recycling, how do you ensure that all the components in the car will be recycled and will not be destroyed at the end of life?
Very good question. As an automotive supplier, we are obliged to make sure that 85% of our vehicle is recyclable. That's going to go up to 95%. In a battery electric era, that's a really interesting question, and I don't think I know the answer, frankly. When the vehicle's on its 10th owner, who is responsible for recycling that vehicle? Is it the 10th owner? Is it the manufacturer? Is it the original purchaser? Is it somewhere in the middle, or is it a combination of all of them? And I don't think I know the answer. When it comes to batteries, for instance, when we're on a battery electric vehicle, there's some really expensive materials in that battery. It's incumbent on our industry to make sure that we're leading the technology that can get those materials out. When we think about this logically, and I believe this to be true, the biggest nickel mine in the world is in Siberia. So let's assume that's off limits for the very foreseeable future, and probably the rest of my lifetime. So we need to find a way of, when those materials are in the battery, we've got to get them out. As part of the work that I've been doing, I've been working with a company called EMR. They're one of the biggest sort of vehicle recyclers in the world. And they understand that they have a responsibility to make sure that we can get those materials out. We need to identify the high cost and the high value materials. We need to be able to separate them from that vehicle so that we can reuse them again as high value materials. For instance, if we're going to use aluminium on a vehicle and we're going to use 6,000 grade and 7,000 grade, we can't recycle that with standard sort of ingot aluminium that we use for the electric motor. It's much more valuable. So we can't just put that in a general sort of aluminium recycler. We need to be able to identify its high value and recycle it at high value. But there is a huge industry working on it. And honestly, I was actually quite surprised and delighted that that organisation and that infrastructure is working as hard as we are to make sure that we can get a zero emission from the whole life cycle.
Okay. Look out, there's for another question. Hey, Andy, did we have one? Yes, we do.
My name is George. I'm a student from KU Leuven, and I have a question for Mr. Reynolds. I wanted to ask him, due to the use of hydrogen, is there going to be a phenomenon of hydrogen embrittlement of the materials used in the aircraft components? And if that's the case, can you ensure that the new materials used for hydrogen embrittlement not to happen, that they continue being sustainable? Thank you very much.
That's another good question. I mean, hydrogen embrittlement is a well-known phenomenon that we will have to deal with, and at the moment, we already see that in some of the technologies that we use today. And without using pure hydrogen, we have to deal with hydrogen embrittlement in a lot of the aircraft that we fly around today. So we have known ways of dealing with that. They're a little bit different when you get to cryogenic hydrogen. Cryogenic hydrogen is actually a little bit more inert because it's so cold. It doesn't do some of the things that gaseous hydrogen does at room temperatures, which is a slight advantage. We have to keep it cold though, which is a big disadvantage. Nonetheless, hydrogen embrittlement is something that we will have to deal with. There's a big balance that we have to try and find, which is as we go towards these very challenging technologies and we try and do hydrogen systems, or we try and take weight out of commercial vehicles, we're pushing the technology down to more and more complicated and difficult things. And sometimes the processes push us towards things which are not very nice. And it's really challenging in aerospace because we tend to live at the very edge of what's possible. And we've done a huge amount of work taking chromates and different chemicals out of our designs. Today, I'm not qualified enough to know about the hydrogen embrittlement processes, so I'm going to resist the urge to try and guess what that is. But I can well imagine that the things that we have to do to protect ourselves from hydrogen embrittlement may not be brilliant. And it's a balance between the environmental benefit against the cost. It will be a very different, I said about there being 1,000 to 1 factor between the manufacturing and the lifetime use. If we can eliminate the lifetime impact, then we will completely change the life cycle assessment of aircraft. And we will have to look at it in a completely different way and start addressing a completely different set of challenges. We will have to do that in parallel to moving towards a hydrogen system. I can't pretend I have all the answers to that question today.
And actually, can I just say, that was a great question, and I'm glad you asked Andy. Thank you.
I made him get the hard one. All right, we have time for one more if there is one. There it comes. This is the last question we have time for.
Hi, my name is Mafalda. I work at Airbus Helicopters. My question is for Andy. Thank you for your presentation. How about implementing this technology in helicopters? Is this being studied? It's in the future plans? What are the thoughts around that?
Well, here we are. I didn't plant that question, honestly. We are, I mean, obviously, in terms of fuel cells especially, there's clearly an opportunity to do something with hybrid energy sources at the scale of helicopters. Many people are looking at that. Airbus helicopters are looking a lot at urban vehicles, which is kind of in a similar space to helicopters. And at the moment, there's a tendency to look at batteries to do that because you can do that for sort of urban mobility vehicles. But as they grow and as their capability in terms of range grows, you'll probably start looking at fuel cells for those as well. And if we can solve some of the challenges that we see in aerospace, in the commercial aerospace, which I'm not saying we've done, but if we can, then it will help helicopters. Conversely, it might be that helicopters get there first, and we start building on the many different companies that are looking at that space and trying to develop aircraft to put something into urban mobility or to helicopters. As you well know, I'm sure there's a huge number of people developing things in that space, and regulators are working on it to try and make that happen. So it may be that they get there first, it may be that we get there first, but clearly there's synergy between the two projects.
Thank you. So that concludes our session today. There's another session coming up at 1:30. So I want to thank again Alan Banks from Ford Motor Company, Andy Reynolds from Airbus for your fine presentations, your contributions to this, and also thank Eric Schreffler from the Michigan Economic Development Corporation and their sponsorship of this session. So enjoy the rest of your show, and we'll see you around.